I'm Ozan Özgür Kaynar. In this demo, I will present my implementation for my project, parameter study for mesh approximation and deformation using list squares. I will go through each feature by describing the methodology with related equations, showing the responsible code segments, and demonstrating the output. In this project, I used an SDK called Open3D, which is an open source Python library for 3D data processing and visualization. So let's begin with mesh approximation. So we can express the mesh in the least square sense by this equation. Also, we can use this equation. So the difference between these equations is the presence of the differential coordinates in this second equation. Uh, in the first equation, it is attempted to flatten or smooth the mesh by minimizing the this term, while in the second equation, it is attempted to match the original differential geometry by minimizing this term. Therefore, the output mesh of the second equation resembles the original local structure, while the output mesh of the first equation is symmetric. So then, I combined these two equations to obtain this equation, where lambda bounded between 0 and 1 is the smoothing parameter. Lambda controls the trade-off between the smoothness and original shape matching. So while lambda is decreasing, uh, this uh, this term becomes more significant. Therefore, uh, uh, the resulting mesh becomes more smoother. While lambda is increasing, this term becomes more significant. While therefore, the resulting mesh matches the original mesh much more. Now let's look at the code. So here, after some calculations uh, for the mesh, uh, I calculate the adjacency matrix and degree matrix, and then Laplace matrix. Also here I calculate the differential coordinates. Then for the least squares equation, we need control points. Therefore, I will use farthest point sampling to find control points. And for farthest point sampling, we need distances between vertices, geodesic distance between vertices. For that, I used the extra short spat algorithm. And uh, so let's look at here, which is the art of the approach. After minimizing the least squares equation, we get boundary vector as lambda times Laplacian times differential coordinates for x, y, and z separately. We get the system matrix as Laplacian times Laplacian, and for control points, we add weights to the diagonal entries of the system matrix, and we add x coordinates times base for boundary x, y coordinates times base for boundary y, and z coordinates times base for boundary z. Then we solve x, y, and z for x, y, and z separately. So here weights are typically 1, but we can change it. Now let's run and here are the codes for visualization and saving output purposes. So let's run the program for some values, some parameter values. So for a number of samples 8 and lambda equals to 0.5, I run the program. So I select the tip of the tail for the first FPS point. So here are the FPS points, and this is the original mesh, and this is the resulted mesh. So let's look at the other results from the report. So here, this is a parameter study for the number of control points. So this is the original mesh, and here the number of control points are increasing in order. So as you see, as the number of control points increasing, the mesh resembles the original mesh much more. And to investigate the effect of the number of control points quantitatively, the volumes of the resultant meshes are compared. So, as you see, as the number of control points increasing, the volume of the resultant mesh converges to the volume of the original mesh. So now let's look at for the parameter study for lambda. So this is again the original mesh, and and this is for lambda equals 0, and this is for lambda equals 1. So as you see, for small lambda values, the mesh is much more is smoother. While for large lambda values, the shape mesh is the original mesh. And also to investigate the effect of the lambda quantitatively, again, the volumes of the resultant meshes are plotted against lambda. So as you see, as increasing, as lambda is increasing, the volume of the mesh rapidly increases, and uh, when lambda is equal to 1, the volume of the resultant mesh is almost same with the volume of the original mesh. So these results are for control points equals to number of control points equals to 32. And as shown previously, while the lambda value is decreasing, the resultant mesh becomes smoother. Therefore, we can use this effect to denoise noisy meshes. A dot mesh is corrected by Gaussian noise of 0.2. Then this noisy mesh is approximated for different lambda values. So let's look at the code again. So I'll change the mesh name, and uh, for I'll use 128 points, and let's make lambda 0 and run the program. So these are the FPS points, and this is the original mesh, which is noisy, and this is the result mesh. As you see, the resultant mesh is much smoother. Now let's look at other results for other values from the report again. So here, as you see, lambda is increasing, the mesh increasingly becomes smoother. Lambda is decreasing. As lambda is decreasing, the mesh increasingly becomes smooth. Now I continue with the deformation part. So for deformation, it is desirable to make the part that is smooth deform smoothly while making the remaining parts match the original shape. And therefore, in the light of equations that I shown previously, I propose a minimization equation in the following form. So here I introduced a diagonal scale matrix K as uh, K is equals to 0 when uh, I does not equal to J, so K is diagonal. It equals to S if I equals to J, and I and J in D, and D is a set composed of the indices of the moved vertices, and it equals to 1 otherwise, and this S is a scale factor bounded between 0 and 1. So by that logic, I decrease the effect of differential coordinates for the deformed part to smooth the deformation. Since the deformed part does not stay the same anyway, we can compromise symmetric for smoothing. However, smoothing is not applied to other parts. Keep the shape as matching as matching to the original shape as possible. So for user sets a handle vertex, and the deformation is applied to the points near handle, and deformation is applied as delta h times t. Delta h is the deformation of the handle, and t is 1 minus d over dmax, and t is the distance of the point I to the handle vertex, and dmax is the distance of the farthest point in the deformed region to the handle vertex. So by deformed, I mean the moved region. And so the deformation function, I define this as a deformation function, and it is linear, as you see. Uh, and let's look at the code. And these are the same with the previous one. So I find near points by this function, and that function finds the near points, a number of near points to the handle. And these are for visualization. And here uh, I introduce S, and differential coordinates for control points becomes S times differential coordinates. And also, uh, I'll show the effect of weights. So I make weights uh, which is previously defined, and I change the weights for control points to 1. Uh, so for other points and control points, I can use different weights. And boundary vectors, again, Laplacian times differential coordinates. That matrix, system matrix, again, is Laplacian times Laplacian. And I input the deformation vector, and I select the handle here. So the select I handle is this. The index of the select handle is this one, and so here uh, these ones are for visualization, and so here again I add weights to the diagonal entries of the system matrix, and again, so let's make the linear one. So this is the linear deformation function, and I here I apply the deformation with these code pieces to the moved vertices, and these are the other vertices. And again, I solve for x, y, and z separately, and these again are for visualization and saving output purposes. Now let's run the code for s equals to 0 point s equals to 1. So again, I choose to handle as the tip of the tail, and these are the near points that will be moved by the linear deformation function, and the handle for I input the handle uh, movement. For x, I'll enter the -3, for y 3, and z 0. So this is the handle, and this is uh, mm, the handle will move from this point to this point, and this is the original mesh, and this is the deformed mesh. As you see, the tail is moved, the tail of 2000, and the other parts are the same. So as you see, the tail is not regular. So uh, not smooth. So we can uh, decrease as I said. So let's make it 0 and run the program again. So as you see, now the tail is much smoother, and the other parts are the same. Now let's look at the report for the other results. So as you see, as decreases, the tail part becomes smoother. The other part does not change. So then I made a parameter study for weight. I changed the weight for other parts. The tail weight of the tail is always one, but for other parts I decrease the weight. So let's look at here. So I make the for moved points the one, but for other points I'll make it. Let's make 0.00. Let's make it 0, and let's make this one. So as you see, the when weight is uh, decreased, the other parts also moves. So the body becomes less rigid. So here this part is pulled, and this part becomes curvy, and this part. So it is basically stretched. Yeah. So let's get the other results. So as you see here for lambda s equals to 0.5, the results, but w is decreasing. As you see, as w decreases, the body becomes less rigid, deforms less rigid, let's say. And as I said, I use linear uh, deformation function, but for linear deformation functions, these end points, which is at the handle, the point that is the region that is distant to the handle, uh, may may distort because of the high variation of the deformation. So therefore, I introduced an hyperbolic tangent function. Used an hyperbolic tangent function, as you see here, the variations are lower, and I will have I will show the effect of the difference of these deformation functions on the mesh. And so this is the tangent of a hyperbolic function. So as you see, so this is this top row is for the linear function and bottom row is for the hyperbolic tangent function. As you see, the hand is distorted for the linear one, but in the other one, there is no distortion in the hand. Also, for weight equals to one, for the linear one, there is artifacts in the armpit region, but for hyperbolic one, there are hyperbolic tangent one, there are no artifacts. But there is also stretching effect in the hyperbolic tangent one because of so these at 10 points the variations are low, but at middle the variation is higher than the linear. So therefore, this stretching effect is observed at the middle regions. So for hyperbolic tangent one, changing this function. I'm changing function here, and let me show it for the Homer mesh. As and let me w equals 0 also. These are the so I'm moving the arm, the right arm to the arm. So this is the direction of deformation. Uh, this is the original mesh, and this is the deformed mesh.